So that we are covering now, it's page 239. So that you can be able to solve Euclidean problems, you need to know these theorems or structures. So okay, I'm trying to open my 239. Please also do the same. If you don't have the book, please tell me, I'll forward it again on the group. If you already in the page, please tell me. You can just show by your thumb. Yeah, you can raise your hand. Yeah, 239, page 239. Okay, so chapter 12 is around Euclidean. So please go to 239. When you are there, please tell me and you can just say we are already there. You can just shout. Yeah. If you don't have the book, please tell me. I'll send it again.
I'm not going to say necessarily the interventions that Peggy said. Let's change a lot of things and I think the way forward.
Please mute Samtanda. Okay, let me send it again. So okay, so once you have opened the book, please tell me so that we can continue. These pages are very important so that you can note which types of structures or drawings to look out for. Okay, I'm assuming everyone is in page 239. So let me just go ahead. We'll just do the structures and explain them clearly. So usually, sometimes you are given this type of structure. Please verify if you can see properly. So you have a circle. You have something like this. So in most cases, they would say these two are the same. This means they are the same. So this angle would be 90 and also this one would be 90. So this means, okay, let's say you have A, B, and C. What you need to note from here, AB is equal to BC. These are the lines, they are equal. And also AC, let's say this was AO. AC is perpendicular to OB. So sometimes you do get questions like this where they want you to find maybe OB, AC. Yeah, so you need to know how to do these types of questions. If you do have maybe in your book or in your past paper a question like that, you can just take a picture and send it in the group so that maybe we can go through it later. Okay, so this is what you should note with these kinds of questions. And another thing, let's say you did have AB and OB and they wanted you to find maybe OA, you would have to use the Pythagoras theorem because you find yourself having a right angled triangle. Okay, let me just have an example. So let's say you had, so this is your circle. This is your center. This is 3. Okay, let's say this is A, B, and C. Then they say this is O. OB is 3. Then they say maybe AC is 6. Okay, so what you need to note here is that you can find AB and BC. It's a matter of dividing it by 2. AC divided by 2 because these two are the same. So AB is equal to BC is equal to 3. So it's 6 divided by 2, which is 3. Now let's say they wanted you to find, let's say the question was find OA. So OA would be, you use the Pythagoras theorem, this is 90 degrees. This would be your y, your x's, and your r, the hypotenuse. So if you were to write it, you would say, you have to say O A, the one that we're looking for, which is a hypotenuse in this case, squared is equal to the other two that you are given, the horizontal and the vertical. So you have AB squared plus OB squared. Then you substitute everything. We do have all our values. So for this one, I took it from my head. So this is the application for these ones. You just plug everything in. So you have OA squared is equal to, you have AC was 6 and AB is 3. You just plug in 3 squared plus OB was also 3 squared. Then you have 9 plus 9, which is 18. Therefore, OA is equal to 18. Okay, OA squared. Therefore, OA is equal to square root of 18. So usually when you are dealing with square roots, there's a rule that says you need to say, let's say you have x squared is equal to 5. Or let's say 9, the number with the square root. Usually when you have this type of form, you usually say x is equal to plus or minus square root of 9. In this case, you don't do that because you are dealing with the distance. There's no need to do that. You exclude the negative. So the distance is always positive. So you shouldn't have plus or minus. You should only have these plus or minus when you are dealing with x, y, for a Cartesian plane, those types of questions. So for this case, you don't need that. You just need a positive value. That's why you just say OA is equal to square root, positive square root of 18. Okay. Since we have covered this one, let's skip let's not skip it. So there is this rule in Euclidean that states that the angle at the center is 2 times the angle at the circumference. So let me just write it down. So let's say you have a circle. Okay, this is your center. So this angle, you need to check where they are coming from. Let's say this was O. The outer one is 1, the inner one is 2. Then this is your A, your B. Maybe let me have another one. Starting from these 2 points, you need to note they are starting from these 2 points. So let me just have the broken line like this. Okay, they meet somewhere here. Let's say this was C and this is C1. So there's a rule in the same page 239 where you have A, B, C, D, and E points on the circle with center O. Then they say O1 is equal to 2 times E. Do you see E that it's somewhere here? So let me just write these letters. This is E, this is A, this is C is here. I'll just write the first one. So this angle O2 is the same as 2 times E1. I hope, I'm sure some of you. Okay, guys, I am recording this. I'm going to upload it on YouTube. I will also send the link to you. Don't worry about that. Okay, so this is the rule when you have the angle here inside your circle. The other one is at the center and the other one is at the circumference. But you need to know they are starting from 1 point. Let me make an example of what I mean when I say they're starting from 1 point. Let's say you have something like this. Right. Then you have something like this, and the other one goes like this. So this is not the case where the angle at the center is the same as the A, is 2 times the angle at the circumference. That will not apply because they are not coming from one position. So you need to make sure that they are coming from one position, like this one, this position. So, okay, let's go ahead and have the other one. And you need to note they really like this type of questions in the exam, whether it's the final exam, where they want you to prove. So as maybe I don't have question papers here, but I will show you later how to prove that. So they really like this question. So we can skip, okay, this one is very important. So now I'm moving on to the next one, where you have a diameter. So the ones that I'm covering is the ones they usually ask. So let's say you have a circle, then you have a center, you have a diameter. Here's your diameter. So if you join 2 chords, so you need to know what's your chord, what's your circumference, what's your radius, all of that, what's a diameter. So a diameter is you coming from one end to the other, straight line. This is not a diameter. This is not a diameter. It has to be straight, passing through the center. And also you're joining 2 radiuses. So this is a diameter. So any 2 chords that meet anywhere, let's say it meets here. So let me draw my chords. Then they meet there. They form a 90 degrees angle. Anyway, let me join the other ones. This one and this one. They also form a 90 degrees. Maybe here, this one, and the smaller one here. This also form a 90 degrees. So make sure that you understand. Okay, so this one, Tula, it's in page 239, and where they say it's the dead one. They say AB is the diameter, then angle C is equal to 90. So your reason for these would be angle in a semicircle. Always. Let's say you are just identifying it in the question. This would be your reason. Angle in a semicircle. Do you understand? Or there are two ways. You can also say chords, subtends, and 90 degrees angle. As you can see in that in the book they showed you, this is another reason. You can say angle in a semicircle or chords or chord subtends at 90 degrees. Or subtends a 90 degrees angle. Yeah, so these are your reasons. Because everything that you do, you need to state your reason. Are you okay, Tula? Okay. So please make use of this book. It's very helpful. Make sure that you use this book in your own time when you are practicing. Okay. Now let's go to okay. Another thing that you should know, the angles that I have covered, I didn't say anything about cyclic quads. The other ones that I have just covered, they have nothing to do with cyclic quads. So now you need to note when I am moving to cyclic quads. So the one that I now have that I'm going to show now, it's a cyclic quad, and you can see, as you can see there, in page 240. So the first one, I'll just write it as it is so that it will be easy with the letters. Okay, let's say you have a circle. This is the case. Okay, something like this. This is A, B. Okay, B is here. Then this is D. This is C. Okay, so for this one, since I'm now moving to cyclic quads, this is a property of a cyclic quad where this angle and this angle are the same. So if you were to write them, you would say angle A is equal to angle B. Then you say the reason angles in the same segment. I'm sure some of you are familiar with this. Okay, let me just cover something before I move on to the next one. So sometimes it happens that they want you to prove something is a cyclic quad. So what you do, let's say you do have something like this, you can also prove with this reasoning that something is a cyclic quad. Let's say you did have this angle and they want you to find angle B. If you are finding angle B to be the same as angle A, then you would be able to say that this is a cyclic quad. So I'll also show you for the other one. So this is the property for a cyclic quad. Cyclic quad. So this cyclic means a circle. So you need to understand that. And quad means four sides. Yeah. Okay. So this is the same segment case. Let's move on. Okay. This one is very important to note because a while ago we did get confused when it came to some cases. I'll show you, but let's focus on this now. Let's say you have a circle again. Then you have, this is your first chord, the second chord, the third chord, and the fourth. So this is A, B, this is D, this is C. This is also a cyclic quad. These are the properties of a cyclic quad. But in this case, these two, when you add them, they give you 180. So angle A plus angle C is equal to 180. But let's say you were having a normal one where these two triangles are the same, like are parallel, two lines are parallel. That's where you would use the cointerior, where these two, they equate to 180 when you add them. So this is not the case for a cyclic quad. You add the opposite angles, right? Okay. So the reason for here, you would say opposite, excuse me, angles of a cyclic quad. You just say opposite angles of a cyclic quad. Okay. So let's move on to the next one. Please give me a second. So the next one, you have an external angle. So this is the one that I was talking about, where we were having like confusion. So it is confused with the tan chord theorem. I'll show you though when we get to tan chord. Let's just deal with this now. Okay, so let's say you have a circle. You have, this is what you have. Then you have a longer one, which has an external angle. So this is C1, C2. Then you have D, this is B, this is A. So note, you have 4 sides for the quads and an external angle. So you have C1. C1 will be the same angle as A. So the reason for this one is an external angle of a cyclic quad. Yeah, so C1, this is your C1, is the same as this one. I will show you how you can confuse it with the other one when we get to that one. So please note for this one. Okay. Then we have, yeah. Okay, so we have a point. Sometimes you do get like find these types of questions. So they are coming from one point. So what you do for this one, these parts PA is equal to PB. And these two are iotangents. So you need to know that as well. Another thing that you should know, let's say you have a circle. So now we have moved on from the cyclic quads. We are no longer like dealing with cyclic quads. We're just dealing with geometry. Okay, so let's say you do have something like this. Let's say you have a radius and a tangent here. They usually form a 90 degrees here and they are like perpendicular. That's what you need to know. Okay, let me now show you the tan chord, the one that I said it's easy to like confuse with the other one. So let's say you have a circle again. You have a tangent. This is your tangent. So let's say you have a triangle inside your circle. Let me name them. So this is B, this is D, this is E, this is A, this is B, this is C. So this is B1. Okay, so this angle here is the same as this angle on this end. The reason will be a tan chord theorem. Or you can say angles between tangent and the chord. And chord. So let me show you how they are different. So you see this one, it's an external angle, yes, and it goes with this one. So make sure it leaves the one that is adjacent to it and it's the same as this one. Make sure that you understand. While for this one, it's the same case, but it's easy to mix up. But this one is just a cyclic quad. You have 4 sides. Here you have 3 sides. You have a triangle. Here you have a quadrilateral. So yeah, that's how they are different. But both of them are external angles. Another thing you should note, this one, it's in a straight line as the shape, in a straight line. And this one, it's in the tangent and the triangle. So you need to know how they are different. Okay. Let's move on. Then the ones that are follows, like, are the ones that we are used to. A straight line, the vertically opposite, alternating for parallel lines, alternating for interior, all of that. So when you are doing Euclidean geometry, it is very, very important to know your simple geometry from grade 9, because sometimes you do not need the complicated things to find the angles that you are looking for. You just use the simple things to find the angles that you are looking for. Okay, is there anyone who has maybe a past paper that we can try, a question that we can try that is complicated so that we can simplify it? Okay, I'll also look for a question here. If you do have a question, you can post it in the group, please. Okay, same book. Please go to page 272, number 8. 272, number 8. Please go to that one, 272. When you are there, please raise your hands. Okay, Silo. Anyone else? Okay, so we have, okay, I can see most of you are already there. Please go to 272, number 8. So for number 8, we have PQR. I hope everyone can see that. Then we have on the other end, we have T and S. Okay, someone needs to be added to the group. I'm not sure who that is. Please tell me your name so that I can know, so that I can forward to you. Okay. So I am going to add you to the group. I'm trying to see. Please give me a second. Okay. Anyone who can identify any angle there before we can do anything? I will read the instructions, then we can discuss if there are angles that you can identify from what I showed you. Number 8. Number 8. So for number 8, we have I will read it out. So we have in the diagram alongside, RS is parallel to QT. So since they are telling us that, so we need to know the rules for angles that are parallel. But let's go ahead. Okay. Okay, please give me a second. I'll add this person. I have included my number in the chat. Please add me so that it would be easier. Okay, now I'm trying to not lose focus. Yeah, please add me. Text me, then I'll add you. Okay, so let's continue. So we have, I'm just reading this. In the diagram alongside, RS is parallel to QT and PR is a tangent to the circle at R. As you can see there, R. Then SMP is a straight line and T2 is equal to X. That's what they told us. So now, since I have covered the basics for your angles, for the Euclidean geometry. Number 1, they say A, with reason, state 5 other angles which are equals to X. Anyone who wants to try, please try it. Okay, someone is saying S1, that is correct. Angles at the same segment, that is correct. Then R3, let's look at R3, yes. Okay, yes, R3 is equal to M1. R3, tan chord. Okay, for the tan R3. Okay, so for it to be a tan chord, it would have to go with both R3 and 4. Okay. Do you understand that part? R3 and 4, when you add them, they can form a tan chord. Okay. Yes, R3 is also equals to T2. Yeah. And M1 is also equals to T2 because you had stated earlier that M1 is equal to R3. So since those two are also equal, then you'll have your X there as well. Do you have another one? Anyone? Okay, so let me just write them down since we have found some of these angles. So we did say they have to be equal to 2. So it's equal to x. Then we said S1 is equal to T2 is equal to x. And it's in the same segment. This is that case. Then we said R3 is equal to T2 as well. I think it's alternating angles because we have parallel lines. Then is equal to x again. So we have 1, 2. Then we said R3 M1 is equal to R3 is equal to x. And is in the same segment again. Then so we have 3. This is 1, 2, and 3. We are looking for 5. So it means there are 5 more which are equal. Do you have Ria, do you have another one? Okay, someone is saying R1 is equal to S1. Okay, let's see. R1 is equal to S1. That is the case. It's a turn code. Yes. That's correct. Are we all happy? If you have a question, you can ask. If you are lost, you can ask. Okay. So let's okay. We have 4 of them now. Okay, yeah. We are left with only 1. So R1 is also included. Anyone who has another one? Okay, let me also look. If you are looking, please state. R1 is equal to M4. R1, what is the reason? Okay, someone is saying M1 is equal to M4, vertically opposites. Okay, no, yeah, that's correct. That's correct. M1 is also equal to X. So are we all happy? Is there anyone who is struggling? If you are struggling, you don't have to unmute. You can just raise your hand or you can type in the chat so that I can explain. So M1 is also M4, yeah. So we have found all our values. Okay, please, Oluetu, if you are not shy, you can unmute so that I will explain. Please unmute and tell me what is giving you problems. Are you struggling? Yes.
La khona usuthi, can you speak Zulu?
Yes.
Okay. Uyabona ukuthi ngithe u-R1 is equal to S1 and then you said turn code theorem. I'm confused there.
You confused?
Yes, lapho.
Okay.
Lokho
Let me just
ngiyakubona.
okay. Okay, let me just have that angle alone. Ne? So I'm going to draw it alone. So we said
this one.
Okay, please mute Oleto. Thank you. So this is our circle. So I'm just going to exclude all the other things and just deal with the angles that we are trying to learn. So we are talking about R1 and S1, right? Always R1 and S1. So this is what we have. Excuse me. Then we have something like this. This is R1. Then S1 is here. Right? Okay, always please unmute so that we can.
Oh, now I
Okay.
get it. Thank you.
Oh yeah, you see it, ne? So this angle is the same as this one.
S1. Okay, thank you.
You're welcome. Anyone else? Okay. So I think we can continue with the questions. Okay. So the second question in the book, we have proof that triangle RTS. Okay. Yeah, is live cursor. We can also conclude that M1 is equal to S1. Yeah, alternating angles. That's correct. Yeah, that's another way. Okay, so let's go to B. So for B, we are trying to prove that triangle RTS is similar to triangle RQM. Anyone who knows what are the properties of similar triangles? Anyone? Yes, all the angles are the same. Let me just go like have something like this, like that. Let's say we have two triangles. This one is big, this one is small, and this one is big. Let's say this was A, P, C. This is P, Q, and R. Yes, angles are the same. One angle from here is the same as one angle from the other triangle. And another thing, there's a ratio, as you can say, as you said live, there's a ratio that if they expand by 2, every side will expand by 2. Okay, let's say this angle is the same as this one. Then you say angle A is equal to angle P. Then let's say this one is the same as this one. It doesn't matter how they are. So angle B from the smaller one is the same as angle. Okay, the first one, angle A is R. Second one is the same as angle P. And obvious, you are left with one from both triangles. So it's equal to angle Q. Yeah. Then the proportion as well. So in this case, since we are doing angles, that is how we will show that these two triangles are similar. Okay, so since we are proving, so we need to show that the angles that are involved in these two triangles that we are looking at or interested in are indeed equal. Okay, so let's identify triangle RTS. So let me try, please give me a second, I'll try and draw this. Okay, I am back. So I have drawn everything. So let's identify the angles or triangles that we are dealing with. So we want to look at triangle RTS. Here is your R. You're starting from here. I hope you can see the blue that I'm writing with. So this is your S. So this is the first triangle. Then let's go ahead and have the other triangle. So we're trying to show that they are similar. So the other one is RQM. So it is the smaller one, this one. This is your R. Do the same thing, just to highlight. So you go with the straight line here. So we are trying to compare these two triangles that they are similar. So as I showed you earlier, usually you have two triangles. The other one is smaller, the other one is bigger. Life also mentioned that there's a proportion that you use to know by how many times are they like bigger than the other one or smaller than the other one. So as you can see here, we have two. The other one is bigger and the other one is smaller. Okay, so since we are doing this earlier, we did say R1 was equal to this angle. This one was equal to X. This is 2. This is 1. These two are equal. Okay, these two are equal. This is X and this also X. But it has no relation with this one, with this triangle that we are dealing with. So we need to check which ones are equal. So you do not assume, you do not like you shouldn't guess. You should have proof. If there is anyone who has the angles that are equal in this case, please tell me before I can continue. So you can just look at what you have. Anyone? Okay, from my side, I can see that M3 is equal to S, all of S, S1 and S2. So let me just write it down. And the reason is a Tan-Code theorem. Are we together? M3. Here is M3. This one is equal to the whole of this one. It's a Tan-Code theorem. Okay, no, I think I'm making a mistake. Sorry, let me check again. Yes, it's a cyclic quad. They are equal, right? Yes, life. Yeah, they are equal. It's a cyclic quad. Thank you. So this one, oh, the problem is the way I drew it. It doesn't look like a straight line. Okay, yeah, this one is the same as this one. Yes. It's a cyclic quad. So it's equal to S, or you can say S1 and 2. Angle of a cyclic quad. External angle of a cyclic quad. So that's your reason. Thank you, Life. Okay, let's check the other one. So we have 2 now that are remaining. So we had said that R3 is equal to X. Also R1 is equal to X. So that means they are equal. So you need to say R3, it's part of this one. R3 is equal to R1. So the reason here it can be like, it's coming from, you remember when they said they want all the angles that are equal to X. So R3 is equal to R1 is equal to X. So these are where all the angles that were equal to X. So they are equal. So yeah, the reason you can maybe support with the other ones. Yeah. Then the other one, so we have Q2 is equal to T1. So it's more of a remaining angle. Do you understand? But you need to show these angles that you are saying are equal so that these can be similar. Do you understand? Anyone who has a problem? Yes, life. Therefore, Q2 is equal to T1, that angle of a triangle. That's a reason. Anyone who has a question or anyone who is not understanding what we are doing? Okay. So the next question is saying, what can you conclude from the fact that M4 is equal to R1? M4 is equal to R1. So what can you conclude from that case? Anyone who has a clue? What is the relationship between the two? Can you see any relationship? Anyone? Okay, we don't have a case where this is an isosceles. This is not an isosceles. Okay. So life, we are doing question 8C. So they because we do know that M4 is equal to R1. So they're saying, what can you conclude about that fact? Do you get that? Yes. So do you have a clue what is the case for this one? From my learner, I think it's a case where, let's say maybe you had a smaller circle. It would be a case where it's a turn chord situation. Do you see that part? Let's say you have a smaller circle. If you have another like a smaller circle, it would be a turn chord situation where the tangent is around M1, M4. Then the other angle is R1. That's what you would have. Do you understand? Is there any question? Okay. Let's see, 200 and, okay, what was 274? Let me check. 72, okay. If RQ is, or a ratio for RQ to RP is 2 to 3, calculate SM, calculate the length. Okay, so for this one, it's for a proportion, so of which we will cover another time. Are there any questions before I end this lesson? So if there are no questions, thank you for attending. I will see you on Thursday. Bye. Yeah, welcome, guys.